my name is Neha, and I'm a chemistry major here at Carolina, just finishing up my sophomore year. And I was actually a peer mentor this last semester for Chem 102, and it was a really rewarding experience. Just explaining things to students and seeing them understand made me feel really happy and like I was positively contributing to their learning. And I hope I can do that this next semester and upcoming semesters, especially with more experience behind my belt and a better handle of how to mentor. The biggest reason why I wanted to be a peer mentor last semester and now and continuing beyond is because as a chemistry major and just a lover of chemistry in general, I want to share my joy for chemistry with others and make it seem like less of a scary thing. I think anyone can be great at chemistry if they put the effort in and have the resources, and I just want to contribute to one of the resources that they have in their learning. So yeah, one thing that I always tell my peers to help them study is to do a lot of practice problems. Learning the concepts is very important, but applying them is a next level step which you need to succeed at Carolina Chemistry and just in the real world. And doing practice problems is how you get that application experience and how you teach yourself to attack more problems. So yeah. The course I hope to peer mentor is Chem 262, so I've chosen a problem from that course, and specifically I've chosen a synthesis problem because this is easily one of the most difficult topics in organic chemistry, and having a systematic way of solving it really helps make it better and less scary. So the first thing I do is synthesis and see what's conserved between the reactants and the products. For this example, we can see that it's the benzene ring. And then the products, two substituents are added on to this benzene ring. So we think EAS because we have an aromatic ring and we have substituents added onto it. And with EAS, it's really important to see the relationship between the substituents. And between these two substituents, we know that they are meta to each other. This is important because the substituents, as is how they are on the product right now, neither of them are meta directors. So this should clue us into thinking, okay, one of these substituents was probably a meta director at first, the other one was added on, and then the original one was converted to its final form. It's likely not the chlorine because if we're thinking EAS, halogenation, it's added in one step, so it's not going to be a meta director first and then convert into chlorine. Chlorine just gets directly added. So we're focusing on this substituent right here then. So how is this formed from a meta director? So biggest thing is looking at the double bond, because there's very few ways double bonds are formed from the reactions we know in Orgo 2. And the biggest thing that comes to mind is Wittig reaction. So for this, we need a ketone or aldehyde, and we need a phosphonium ylide. So we would need something like this. To get the double bond in the right spot and in the product. And this checks off all our boxes. The ketone is an electron withdrawing group. It's a meta director. So if we had that, we could add the chlorine meta. So that's great. We have the last step in our synthesis. So now let's kind of work forwards. We worked backwards. Now let's try to get to that point. So how do we get a ketone substituent added on to a benzene ring? So we're thinking EAS. And a way to add a ketone through EAS is Friedel-Crafts acylation, where you have an acid chloride, AlCl3. And the acid chloride would have the same number of carbons, so it would look like this. And then we have AlCl3, and then we have an H2O workup. Do not forget the workup that is needed to remove the complex. So this allows us to add a ketone with the same number of carbons onto the benzene ring. There we go. And now we have the meta director needed to add the chlorine meta. So we do this through another EAS reaction. This is halogenation. You would get this intermediate. And now the final step is something we already talked about, turning this ketone into having a double bond. And this is the Wittig reaction that we discussed before, and we already have the reagent selected for it. And now the synthesis is complete. So there you can see how we broke down this complex synthesis into a series of steps, working backwards at first and then seeing what we need to get to that point. And it's really a lot more clearer than it was at first.